Okay, Shweta, I'm going to hand it over to you.
Thanks, Elsa. It seems like I'm having a technical issue with the slide sharing, so I did share that with you. If you can share it for me, that would be great. Sorry, everyone. We are just having a technical difficulty.
Give us one more minute here while we get everything connected, everybody. Thank you for your patience. Shweta, why don't we go ahead and get started and we can add the slides in as we catch up to you?
All right, that sounds good.
Thank
Hi.
you, everybody, for your patience.
Sorry about that. I'll try to be cover the topic in the interest of time, but as we cannot see the slides, I'll try to restrict the technical content to be discussed later. So yeah, hi, I'm Shweta. I'll be talking today about the word embeddings journey and the transformer, which probably anybody who is familiar with natural language processing would have heard recently their success. So I'll be covering today the journey, which basically is from the traditional approaches where we used to represent text in terms of the frequency or the count, and move towards talking about the state-of-the-art approaches where we use the complete corpus's contextual information for representing the meaning of each word. So we'll be talking about uh, various different textual representation. But first, let's discuss what the word embedding is. So, based on the Wikipedia definition, that in NLP, word embedding is the term we use to represent words for text analysis. We know that machines are good in understanding real value data as compared to the textual information. Text is nothing but a way of communication between the humans. Hence, that language is not understandable by the machines. Hence, we wanted to convert our text into a vector space of a real value so that the machine can understand and represent uh, that language which we humans understand for various different applications. And these applications are not limited to word similarity or machine translation. They have a wide amount of real world applications, be it sentiment analysis, co-reference resolution, clustering, or maybe like semantic understanding of the documents, large amount of documents or corpuses. So we know that languages can have a meaningful impact, but how do we make these text data being represented in terms of a real valued vector, which machines can understand correctly what we mean by a corpus? Hence, word embeddings becomes really popular, and the journey has been widely divided from uh, count-based methods where the data, as I said, or the content being represented in terms of whether this particular word has occurred in a corpus and how many times it has occurred in a corpus. So we will talk about the journey from like a word to vec model to glove model, and today's contextualized word embeddings, which are basically Elmo, GPT, BERT, or different flavors of BERT and XLNets. So in the traditional approaches, we used to have bag of words, which is basically nothing but a unigram model. The terminology that I used is unigram, which is 1 gram model, where in a sentence, uh, let me see if the text is there because I just get the notification. Okay, sounds good. So can you move to the next slide? One after that. Yeah, so I've been referring to this the word embedding journey, where initially we used to represent the words in terms of count representation of each word occurred in a sentence. And because we know that the vocabulary size is really huge, we wanted to do a dimensionality reduction of our matrices so that we can get the meaningful information represented in a text rather than having a really large vector to represent the word which loses its information. And from there we move towards the more of a context based representation, and you can see that the timeline has kind of varied a lot from 1988, where we used the LSA or LSI to represent the sentences or the text, and till 2013, where the modeling or the neural networks or the AI or the machine power has become really strong, that we'll be able to grow from 2013 to 2018, where as of today we can see that we can actually able to represent the language overcoming the human limitations. Kelly, can you move to the next slide? So the bag of words model, which I was talking earlier. So in a sentence, here we have a sentence which is, this movie is very scary and long, and not slow is spooky good. So there are different words which the sentence is talking about. And these are basically coming from a different reviews. And this is what representation look like, that each word which is occurred in a sentence being represented as like a corpus vocabulary. So this vocabulary is limited, it's 11 words, but you can see as the text grow, this matrix is going to grow. The another representation could be like an n-gram, where rather than representing individual word, we represent a single word as a combination of words. So this movie, if coming together, that become a 1 gram, sorry, 2 gram for representing, and that n number can vary. So there are different ways of representing bag of words, which is numerical representation. There is another traditional approach called TF-IDF, which people know as like term frequency and inverse document frequency model, where we use the information of different documents. And for a single word, we compute that based on how many times a single word occurred in a document. And that is being multiplied by how many times this word occur in a document with regards to all the documents. So this is the formula which has kind of given a much more meaningful information across different corpuses, but it is still limited to computing each and every word frequency and sort of just representing at the end a single word. Let's move to the next slide. So yeah, in the past, which I have been talking about is the large corpus. And as the corpus vocabulary increases, our metrics becomes really large. And and most of these sentences or reviews or any content within a document uses a limited set of words. Hence, our representation in the metrics is going to be really sparse. So we wanted to perform a dimensionality reduction, and SVD has been really popular in reducing the document representation in the high dimensional space to convert it into a lower dimensional space, keeping the information intact. So this is what it looks like, where the if you are looking towards the embedding, you can just look at the encoding of the top words. And but if you are interested into converting the meaning of a single word, you can embed that information by decoding the representation. So that's been really popular till 2013. And let's move to the next slide. But in 2013, around that time, machine power has become really popular, and word-to-vec model kind of came, where the question become, can we incorporate a contextual information? Contextual information basically means what word precedes or follows it as the information to incorporate what is the meaning of this word. So there have been two models being published. One is predicting a word given its surrounding context, which is known as the continuous bag of words. And the another have been the skip n-gram, which is basically given a word, can we guess what could be the preceding word or the following word for a different context. So these are the two representation. These indexes -2, -1 are against a particular word within the sentence. So let's say your sentence is this, where you are trying to, in the CBA model, you are trying to predict the probability of this word, which is the Seattle. Can you predict Seattle given raining in and throughout this? Whereas in the skip n-gram, you have been given Seattle and you wanted to predict one by one words such as raining given the Seattle, in given the Seattle, throughout given the Seattle, and so on. So this is with regards to the window of 2. You can increase and decrease the size of the context, but still it is incorporating the local information. Let's move to the next one. Because right now we are only talking about the local information, we kind of loses the overall global context, the theme of the document. Hence, Glove model, which came out by Stanford, kind of incorporates the information from word to vec, which uses the word representation in a vector along with the co-occurrence matrix, which stores the large amount of information across the document. And you can see that from this graph on the right that the clusters of different nodes of the same color, they kind of incorporates the similar meaning. And this has been achieved by considering the example presented in the paper. When you are looking to predict a word K, K could be solid. If it is solid, given a ice, it has a higher probability as compared to the where you are predicting a word gas given the ice, because ice represent the solid form as compared to the steam, which is the gas form of a water. But water and the solid has a high probability as compared to the gas. And fashion is just a random word they use to get this probability, and kind of shows that it kind of incorporates the global information, what is the meaning of a word. So let's move to the next one. But you can see that in the beginning, we have been kind of still dealing with a large amount of corpus, but around in 2015 and so, RNN and LSTM for text data representation become really popular, and hence the language models come into the picture by using the LSTMs. Also, we know that the RNNs and LSTMs kind of are slower to train. So these models also require a lot of processing power, but the idea in the Elmo model, which is basically nothing but an embedding from language model, it uses the bidirectional LSTM. So as you pass the sentence, it looks from the back and also processes the information from the front. So if your sentence is let's stick up, you are kind of passing one embedding at a time and kind of predicting the next word given the previous, and you are concatenating that embedding learned at each layer together to represent the representation of a single sentence or a single word at the end. And this is kind of like a architecture on top of which different different new architecture have been built. So let's move to the next one. Transformers. So this is where the most of the today's research lies in. Transformers uses the encoder-decoder architecture where we read the sentences from the beginning, and encoder layer kind of represent the information learned from the text, and decoder part kind of tuned to translate the information learned from the encoding to a particular output, or output could vary based on the problem at hand. So the main important thing is what these encoder and decoder block contains. These encoder and decoder block contains two information. One, what is the position of a single word where we wanted to pay attention. So attention basically is when I say a sentence, how much emphasis is given to a particular word given the text I have been spoken by a human. So we as a human understand a sentence that where the pressure or emphasis has been given in a sentence, that information is added with this architecture within the each encoder or a decoder block. They are very similar, but initial embedding kind of computed by applying this self-attention and concatenates for various different words in a sentence. Once you have that information, you passes it along to a feed-forward neural network to kind of learn from these representations, and at the end normalizes it. The one thing to note in the transformer, we use a layer normalization rather than a batch normalization, which is across the features, then across the rows, which is the sample. This is the general architecture. And the good thing is you can see there are a lot of the aspect which can be run parallelly. Hence, they become really popular. And on top of this architecture, we kind of built GPT model, BERT model, and so on. So let's move to the next slide.
Hi there. Just wanted to give a quick update. I know that the slides got going late and this may have delayed your schedule a bit. We're going to extend the time of the session just to tell everyone, the lunch and learns will still start at noon. So if you have to leave early, always you're available to come back to view the recording. And you can post your questions in the Q&A now and see Shweta's answers after the session. Sorry to interrupt.
Let's move to the next slide. So yeah, what I've been talking about, like on the general architecture of transformer, GPT and the BERT kind of come out. GPT focuses on the decoder model to decoder side of the transformer to fine tune on a particular problem, whereas the BERT uses the encoder aspect of the transformer to represent the context or your corpus. And there have been like a various different flavors of BERT and GPT came out, as you can see, but the main variation have been in terms of the number of parameters, number of layers of encoder or decoder, and how many nodes within a single layer have been these different architectures have been trained on. And as you can see, the number of parameters are in the order of millions, be it GPT or be it BERT. It requires a large amount of corpus to train. Hence, these models have been pre-trained, and in your practice, you can use those pre-trained models to fine-tune on a particular problem, and hence these becomes really popular as of today, because you do not need to do the full training, which sort of requires a really large amount of corpus, really large amount of resources, as well as a very specific hardware on which you can actually train these. So let's move to the next one, where we'll be talking more about their architecture. But on the left side in the image, we have the GPT model architecture and how it is being used for a particular problem. So you can see in the classification task, for an individual text, you add the beginning and the end, so that your sentence, when you are passing, the model kind of knows where it is starting from. And once you have the representation, you apply a transformer to learn the representation. It's a classical classification task. So you wanted to predict the label, hence a linear layer has been added on the top, so that you can predict the probability of one class over the other. And you can see the same architecture can be used by changing the input representation and the architecture. They have been combined to sort of use the similar modeling design for different natural language and processing tasks, be it similarity identification between the two tasks, two sentences where you can change the order and pass it along, or be it a multiple choice question. So this is the GPT where you are fine tuning for a particular problem. On the right, we have a BERT. And in the BERT, two things are most important. One is like how an input is represented, which is passed along for encoding. You need an initial token encoding, which you can use traditional approaches or early embeddings, simpler embeddings to represent the text into a numerical form. You add a segment information on that vector to incorporate the information, whether it belongs to a sentence 1 or a sentence 2. And it also asks you to apply this positional encoding to represent whether this word within a sentence occurs at the first location versus the any location. So kind of like the position gives you the contextual information. And when you apply this, BERT kind of trains and learns a representation, which is the embedding. And that embedding can be fine-tuned. Once you have the pre-trained model, you can fine-tune that on any problem, as the single embedding kind of learned the overall context information by applying the self-attention and the transfer learning. A lot of these components you can see can be trained parallelly, hence it's the benefit. But in the BERT, we apply a lot of the sentence manipulation, because when you are passing a large corpus, you do not have a fine-tuning objective. So what it does is it applies some of the masking techniques to change the data set. So let's say if you have a sentence, like in this example, my dog is cute. So if you are passing this sentence, you will be masking randomly selected words. And your objective during training, pre-training step kind of becomes predicting those masked words to kind of pre-tune your data set. Hence, this is not something really popular in the real life. So kind of you are losing some of the contextual information when training. Hence, let's move to the next design architecture, which is XLNet. And in XLNet, it basically says why to mask something where you can actually train your model on different permutations of your words within a sentence. So it kind of overcomes that by applying different permutations, and that permutations be it so let's say you have a four word sentence. This is me, this is just me, these are four words. And so this outer loop is basically your estimation, your expectation against each of these permutation, and within each permutation you are trying to predict the probability given the words preceding it. And hence there are four different combination embeddings you will learn, and you kind of tries to maximize. This becomes the objective of the overall training. And you can see from the result here that XLNet has kind of overcome the performance of BERT large by a significant difference on various different NLP tasks. So this is kind of as of today, which comes in, I think, 2018, late 2018 and early 2019, this XLNet has been really popular, but it requires a really large amount of training as compared, or training or the training resources as compared to even GPT and BERT model. So at last, I'll be talking about where the BERT as of today exists. So in the next slide, we can see we have various different flavors of the word which have been fine-tuned on a particular problem by various different companies who have the computing resources, and they have kind of trained and tries to overcome some of the limitations of the bird, and they have different distributions which are currently available. Ernie, Roberta, Albert, Distill A are few of the popular, and you can see they are kind of lies within the 2018-2019 timeline. And as of today also, this research has been continued, and we are still seeing a lot of different variations, but these models have been used for word representation or textual problems as of like kind of a black box, and they have been ability to fine tune, which is as the today's representation of the data where this word embedding lies. So that's all I have for today. That's where I sort of end. The next slide, I just tried to combine all the resources which helped me understand these. Most of these are the papers, but some of these are some of the articles. I would, if you are interested in any of those to go into more details, I would appreciate if you can follow these links. And at last, I am open for any questions.
Thank you so much, Shweta. That was awesome. And I will post your email in here for participants who have to leave for the networking. And she's also available on Slack if anybody wants to reach out to her there. And maybe you can post these resources there and we'll have the recording available later. Does anybody have any questions that they would like to post in the Q&A now? It was a lot to cover. It was really neat. NLP is very fun. I'll give people one more minute, and if there's no immediate questions, everybody might need a chance to let it all sink in and then get back to you, Shweta. Thank you all again for your patience today and for joining the conference, and an awesome presentation. Feel free to follow up with Shweta on Slack or with her email, which is in the chat here. And with that, we're going to conclude this session. Thank you so much for your time today.
Thank you, everyone. Thanks, Elsa.